I am recording. Now, I just want to point something out to you about this one. That's why I haven't erased the stuff. Last time, in looking at this problem, where we're given two sets A and B of numbers, and A is non-empty and B is bounded above and A is a subset of B, explaining why sup A and sup B exist involves some observations why the two sets have to be non-empty and the two sets must both be bounded above. Now, A is given to be non-empty and A is a subset of B. So because B has a subset that is non-empty, obviously B is non-empty. All you have to do is choose a member of A and say, you know what, this thing is in B, you see? Now, why is B bounded above? I gave an instruction there. Make sure you can understand why every upper bound of B, and by the way, B does have upper bounds. How do you know that B does have upper bounds? Because it's given that B is bounded above, right? Thank you so much. I said make sure you can see why every upper bound of B has to be an upper bound of A. Now, this required a proof. How do you prove for every? What's the first word in your proof? Suppose. Suppose that W is an upper bound of B. You understand? Now ask yourself, what is it that I've got to prove? I've got to prove that W is an upper bound of A. Ask yourself, what does that definition say? You've got to know immediately. If I say, what does it mean when you say that a number is an upper bound of a set? You must be able to rattle it off straight away. It means that every member of the set is
less than or equal to that.
Less than or equal to, right, so how do you prove for every? Suppose that X is in A. You understand? Now you've introduced an X in A. Well, that X has to be in B, not so? Therefore, X is to be less than or equal to W. You understand? That's how you begin. Do that. The rest will follow, and give it a bash. If this is worrying you, look for some others where I've written it out in full and rewrite those. It'll get you over some very bad habits. And then you'll be in a position, sometimes you'll write to me and you'll say, look, I can do this, but now I have no idea what to do. I cannot see what to do. Lots of people have told me that. Then I've said, okay, I'm going to show you how to get going. You see, it's a lot easier for me to do that than to write a zillion corrections when you write all sorts of completely crazy things, and I fill your document up with zillions of comments and everything, and I spend ages and ages on it. And sometimes I've done this telling you certain things that I know I've told you before in earlier documents, and you haven't taken notes from my earlier comments. You're making me write the same instructions again. I don't mind writing to you, but please look at what I send you and use it before you send the next thing. And above all, rewrite the proofs that I do until you can do them you're alone, closed book, not at the same time. Maybe an hour or a day or a week later, you can say, I know how to do that thing, and you can write it and feel it. You are the author of it, even though you got it from me originally. That's the secret. Okay? So I'm going to move to exercise 4. I know that help was provided. I managed to put stars on the ones for which there was help provided, but I still want to say something. It is given that A and B are non-empty bounded sets. So it's given that A is non-empty and B is non-empty. And it is given that for every X in A, there exists a member of Y such that X is less than Y. You know what this is saying? You know what this is really saying? A member of A will never ever be an upper bound of B. That's what this is saying. For every X in A, I'm giving you a guarantee that X cannot be an upper bound of B because there exists a member of B that is bigger. See? And I'm also telling you that for every Y in B, there exists x in A that is bigger than y. You see? So we're going to talk about this problem. Now, I don't have to justify why sup A exists and why sup B exists, because it's given that the two sets are non-empty and bounded. You know, bounded. I could have said bounded above. I got lazy, because below is not of issue here. Okay, and we want to prove that sup A is equal to sup B. So the first task, I'm making a breakdown of this. I will show that sup B is an upper bound of A. I'm making an announcement in advance of what I'm going to explain. You know, I want to tell you something. We're explaining things. When you're doing baby algebra in the 10th grade, you should also be explaining things. Some of you think that you suddenly come here and for the first time in your life you're writing proofs. Not so. You've done thousands of proofs in your lives, but you just don't realize. You don't realize how many times you've written something that was a proof and you didn't call it a proof. And I wish your pre-calc course had been taught correctly. You'd find the atmosphere here much better. Trouble is, if you're cranking things out and getting answers to put in boxes at the end, or using some dreadful software product that works you through a sequence of working steps, people who should be making fries at Wendy's teaching mathematics. Anyway, I'm going to show you that sup B is an upper bound of A. I'm making that announcement. You understand? I'm not ready to do it yet. In fact, I think I'm going to change color. I'm going to put my thoughts in that color. And I'm going to tell you what it is that I need to do. I need to explain why, or what does it mean to say that sup B is an upper bound? What does the definition of upper bound tell you? A number is an upper bound of a set when what? When every member of the set is less than. Aha! I need to explain why the inequality x less than or equal to sup B must hold for every x in A. You understand? I'm telling you something that the proof that you're going to write depends on your knowing what it is that you want to do. If you know what you want, you have a chance of getting it. If you don't know what you want, and you're just writing randomly, the chances are that you won't get a proof. It was Arthur Eddington, a long time ago, who posed that there is a very small probability that if you put a chimp in front of a computer, not a computer, he didn't know about a typewriter, and let him type at random, that he might type Encyclopedia Britannica. It could happen, you see. It probably won't, but it might. Yes, sir?
Can you make the font a little bigger for the stuff under the writing?
How about if I do that?
That's much better.
Okay. As long as I remember to put it back at the end.
I heard it was the entire works of Shakespeare. For the moment.
Oh, maybe it was. Yeah. Anyway. I need to, I think it's harder to type Encyclopedia Britannica. I was thinking of the Red-Headed League, actually. Anybody know about that? I've got one ahead of you here. All right. So Okay, I need to explain why this inequality must hold for every x in A. I'm ready to begin. How do you prove that something happens for every x in A? Suppose what? Suppose, you want to prove that something happens for every x in A. Suppose that x belongs to A. Okay? That to prove for every, say, suppose. Let me give you the basic story. To prove for every, you write suppose. To prove existence, give an. Who said choose? You're wrong. Who said choose? To prove existence, you give an example. Show one. Okay? To use known existence, you say choose. And what does it mean to be making a definition? You're making a definition when you say we define, we write. That's when you're saying precisely what you mean by something. If you want to say, I am defining x to be 7, that's a definition. You can't say, I'm defining x to be a positive number. Some of you want to take 6 months off my life. You say, I'm defining x. There are lots of positive numbers. That's not a definition. A definition, you're saying exactly what it is. Okay, all right. So suppose that x belongs to A. Now, what do you know? What do you know goes on when you have an x in A? There's information. You're told that for every x in A, something exists. Isn't that right? And when something exists, you can say choose. So what can you choose? Choose a member y of B such that what? X is? Actually, you can demand, less than or equals correct, but less than you can have. Might as well take the kitchen sink. See? Go away. Let me just close this. Outlook drives me crazy. Okay. So now, choose that. Now we can see that x is less than this element y that I've just chosen, which is less than or equal to sup b. How do you know that? Because sup b is an upper bound of b. You understand? So now I have shown, as I promised, that every member of A has to be less than or equal to sup b. As a matter of fact, I've got more information. I even know that every member of A is less than sup b. See? That's even more. Okay. Now, please prove that, wait a minute. I'm going back to this field. Please prove that every, please prove that sup A is an upper bound of B. The proof is pretty much identical. You just interchange the A's and the B's. It's the same piece of mathematics. Okay? I ain't writing it. Okay? But you do it. Now, how do you know that these two things must be equal to one another? I'm going to say it, but I'm not going to write it. You see that number over there? We have made the observation that this little Charlie over here is an upper bound of A. Isn't that right? On the other hand, this thing is the least upper bound of A. The least upper bound of A can't be more than some other upper bound of A. Do you understand? If I take the youngest person in this room, that's me, right? Then I can't be any older than anybody else in the room, right? Maybe I should have said oldest. Anyway, we can dream. So the fact is that because sup B is one of the upper bounds of A and sup A is the least upper bound of A, this must be less than or equal to this, right? Now let's talk. Sup A is one of the upper bounds of B, and sup B is the least upper bound of B, so therefore sup B is less than or equal to sup A. So now, because the one is less than or equal to the other, and also the other is less than or equal to the one, therefore the two have to be equal to each other. Okay? So, there it is. I've started it. You finish it. Exercise 5. A and B are given non-empty sets, and for every x in A and every y in B, x is less than y. There's an ingredient in this proof that really is somewhat similar to the stuff we did together on the infimum version of the completeness axiom. You know, when I wrote that, I took almost a whole hour to teach that proof to you. Do you remember? You should have spent most of your time rewriting that proof and rewriting. When you've rewritten it enough times, or one more time. See? When you're really sure you've done it enough times, do it one more time. Rewrite it until you can do it, closed book, on your own, and you really feel that you could stand before an audience and explain and get good scores for your teaching of it. That is the key to understanding mathematics. Imagine that you have to teach it and really explain. Never say anything because it's what you're supposed to say. If you ever say something because you think that's what I told you you must say, you are wrong. You've got to say it because that's what you want to say. So anyway, this thing has some ingredients in common with that. We're given two sets A and B, and we're given that for every x in A and every y in B, we have this inequality. I'm going to change to this color, and what did I do?
Something from the previous class? Hit Control V accidentally?
What did I do? I have no idea. So anyway, I want to explain, and this is the sort of thing I did the other day when we did the infimum version of completeness. I want to explain why every member of B must be an upper bound of A. I'm going to explain this to you. Okay? Here's the yellow. I'm about to start. What must I write to prove that every member of B eats sardines on toast? Suppose that Charlie belongs to B, right? What letter should we use? I don't care what you can use, any letter you like, except a capital A or a capital B. They're in use, right? Okay, suppose I'll use a Y. Suppose that Y belongs to B, period. Okay? Now, wait a minute. I'm going to think aloud. My job, my task, if you like, is to explain why we must have x less than or equal to y for every x in A. Isn't that right? Right? Well, I want to tell you it's not much of a task.
It was given, right?
It was given. You were told that whenever x is in A and y is in B, x is less than y. So you've got an element y of B for every x in A, x will be less than y. Not much of a task, you see? Right? So I will just tell you, since x is less than, actually less than, no more than this, y, for every x in A, we know that y must be an upper bound of A. The original task to prove that every member of B must be an upper bound of A. Have we proved that? I said, suppose that Y belongs to B, and guess what? It's an upper bound of A, right? Now for you, please explain why every member of A has to be a Lewin. No, what begins with L? Lower bound of B. You understand? How would you prove this? Suppose what? Suppose that X belongs to A. And then you need to prove that for every Y in B, X is less than Y. Not much of a task. It is given. See? Right. Now I want to tell you something. Now, given any member Y of B, since Y is an, I will emphasize, an upper bound of A. Haven't we just proved that? Or made that observation? Yes? And sup A is not just any old upper bound of A, it's a very, very special one. Sup A is the least. Sup A is the least. Nah, let's write it this way. The least upper bound of A. You want to know how you type that stuff? Please. It's called emphasized. You go down here. You want a keyboard shortcut? Should I tell you? It's F6. Because I happen to, and I want to tell you, if you open a brand new document, it will tell you somewhere in here. I thought it did. Could have sworn I put it. Yeah. No, I didn't. That was for the yellow.
Alt 3 is what came up as a...
No, F6. I guess it was a secret. Anyway, all right. Let's get back to the math. Given any element Y of B, Y is known to be an upper bound of A, and sup A is the least upper bound of A. Since that, we know that sup A has to be less than or equal to Y. Reasonable? Yeah. The least upper bound can't be more than some upper bound. Okay? Therefore, you say therefore in order to make a conclusion. Okay? When you say, I am going to conclude from information I have at my hands that something happens, that's therefore. Therefore, sup A is a lower bound of B. Look, for every Y in B, sup A is less than or equal to Y. You understand? By the way, the wording is, you didn't have to do this, this wording. You could have said, I'm making an announcement. I want to explain why sup A is a lower bound of B. Suppose that Y belongs to B. I know that Y is an upper bound of A, and sup A is the least upper bound of A. Therefore, I've got that. See? Okay. Since sup A is a lower bound of B, and inf B is the greatest lower bound of B, since sup A is a lower bound of B, and inf B is the greatest lower bound of B, what do we know? Sup A must be less than or equal to inf B. Is that what it asked us to prove? Right? Then I said, by the way, it is possible that they'll be equal to one another. Give an example. When do you ever give an example in mathematics? To show that something can happen. To prove existence, you see? To prove the existence of two sets for which you get an equal sign, give an example. And I will leave that open to the floor. Find an example. Okay, number 6. Number 6, I know I've got to do this problem. A and B are non-empty sets of real numbers, and sup A equals inf B. Given. Do you understand that it's the special case of what was going on here? You see? And the top of the set A is the bottom of the set B. You understand? Prove that for every positive number delta, don't even read it. Prove that for every positive number delta, blah, 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 blah. I'm not even reading. I don't want to know. How do I write the proof? I want to prove that for every positive number delta, suppose that delta, I'm going to give you what is called a positive sign. What does a positive sign look like? That's a positive sign, right? Less than 0 is called a negative sign. Don't you ever refer to a little horizontal line used for subtraction as a negative sign.
It's a minus sign.
You have been subjected to abuse by Wendy's workers. You have to get out of it. Right. Anyway, now, suppose that delta is positive, right? Greater than 0. Well, it's about time I read what we have to do. It is possible to find a member of A and a member of B doing some job. Ooh. I've got to give, to prove that something exists, I've got to give examples, right? This is a hard proof. This is definitely a hard proof. But I want to tell you something. In mathematics, there are no ordinarily hard problems. There are very, very, very hard problems. And there are easy ones. There's nothing in the middle. There's no problem that's just a little bit difficult. A little bit difficult is like being a little bit pregnant. You don't ever have slightly hard problems. At the moment you understand any problem, it's easy. And until the moment at which you understand it, it's a killer. You see? If I tell you the number of times in my life I've been looking at something and battling and battling and battling, sometimes for years. And suddenly one day I'll say, you know, this stupid problem has been so easy. And send it to a journal, get a publication, because other people haven't seen it yet, and they still think it's hard. Okay. This proof for the moment is diabolically difficult. To get an example of a member X of A and a member Y of B doing that job, well, I'm going to break the logjam for you. That's why you still need me in your life. You see, there'll be a time when you be free of any need for Lewin. For now, you need my help. Maybe. I might be stealing this from you. So here we go. I'm going to tell you that since this number, that number stands for the greatest lower bound of B, right? And if you add delta, that's greater than inf B. Do you understand? I'm going to apply what I call the BMW argument. this number is greater than the greatest lower bound of b. If you are greater than the greatest, you're not one of them. Isn't it right? Since inf b plus delta is greater than the greatest lower bound of b, we know that inf b plus delta cannot be a lower bound of b. Do you understand? When you know that a certain number, Charlie, is not a lower bound of a set, what is it that you know? A number fails. Okay, let's talk. I tell you, everybody in this room can speak French. That may or may not be true. It's false, actually. Everyone in this room can speak French. The denial of that statement says what? At least one person in the room cannot speak French, right? Reasonable? What does it mean to say that a certain number is a lower bound of a set? It means that every member of the set is greater than or equal to the given number, right? What does it mean when you have a number that it fails to be a lower bound of a set? Fails. It means that there exists at least one, right? At least one number that is less. Well, when you know that something exists, what's the next word in the proof? Choose. Now I can tell you, choose a member y of b, and after the words choose, you very often writing correct spelling helps. Such that. Please be careful. Such that is a qualification. It means, if I just say choose a member y of b, it could be anywhere, you see? As long as b is not empty, you can do that. But if I say choose a member y of b such that y is a millionaire, then you need to know that there are members of b that are millionaires, you see? Choose a member y of b that loves me, right? Since nobody loves me, that's a very difficult choice, you see? So, okay. So I'm saying choose a member y of b such that y is less than this number, inf b plus delta. The number inf b plus delta is known not to be a lower bound of b. What does that mean? There exists a member of b that is less. When something exists, say choose. Okay? Now observe. Please observe that y minus delta is less than inf b, right? And it's about time I use the given information that inf b is the same as sup a. Okay? Let me just rewrite this equation. This inequality, I mean. Yes? This number y minus delta is less than sup a. What does sup a mean? Sup a stands for what? The least upper bound of a. If you are less than the least, then you don't live in the southeast, right? I mean, right? If you're less than the least, then you're not one of them, right? You're not an upper bound of a. So let me say so. Therefore, y minus delta is not an upper bound of a. You understand? Okay, what can you do with that information? A certain number is not an upper bound of A. What does that mean? There must be at least one member of A that is bigger. Well, when something exists, you can say, choose a member X of A such that Y minus delta is less than X, and I believe I have now given you an example of a member of A and a member of B doing this. Reasonable? This inequality. Quickly give you that one. See? Okay? Now, do you understand this proof right now? Hell no. If I was sitting listening to somebody explain it, even me, no way would I understand. The only voice you can ever hear is your own. You have to take this thing and you have to write it yourself. And you won't be able to write it yourself without first having my help. And then you put my stuff away and you think about it. You know, I want to tell you, I know you're dying to ask me a question. I'm going to keep you waiting for a minute. Sometimes the best way to come up with the proof is to walk away from the desk and think about it and write it in your head. There have been times when I'm thinking, I'm looking at something, I just can't see it. And later on, I maybe in the shower or something, I'll say, I can see this now. There was one particular time when I was teaching something and I had to give a proof of a hard theorem. Steve and I, he was my student, we'd been sitting and drinking large volumes of coffee. And one of the basic laws of physics says that if you drink coffee, things happen to you. You know, so I had to excuse myself and go downstairs to the men's room. And it was very fortunate because I didn't have a clue how to prove that theorem. But standing there in the men's room looking at the wall, suddenly I was able to see that theorem. It was so obviously, came back and said, okay, Steve, let's do this proof. And I wrote the proof for him. Tell you, I always knew it was good to drink coffee. So I hope you don't think I'm being too vulgar here. But, all right, so, yes, sir, proof, a question, I mean.
Okay, so for this proof, do you have to make it abstract, or can you, like, choose an example where you design your own set A and B?
Well, you must say all this very, very slowly. I didn't follow a thing you said.
Okay, so with this proof, you found an example, but you made it abstract. Can you, like, actually design your own sets A and B and try to prove it that way, how it would work?
Design your own sets? You mean give examples of sets? Oh, no. This is a proof of a for every statement. You see the word suppose? If it said, prove that there exist sets A and B such that something, 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 then you've got to give an example of a set A and a set B that do the job. You see? But you can't give an example to prove a for every statement. Oh no. You give an example to prove existence. To prove for every, say, suppose the problem started with a suppose statement. We are proving a theorem that says, for every situation in which you have two non-empty sets called A and B, or whatever you want to call them, with the information that they're non-empty and sup A is equal to inf B, given, something will happen. That for every delta greater than 0, something will happen. You see? So of course you can't say, I want A to be something. No, you can't. Because what if A is something else? Absolutely not. Give an example to prove existence. Okay, well, I guess that I'm not doing all the problems, but I've done some of them, and you must rewrite mine. I will tell you, though, that exercise 8, there will be a place in the not too distant future where I'll do something that will eat this thing for breakfast. But anyway, and 19, I don't know what the hell is going on here. I don't know. I'm not sure what I intended to write, but anyway, to save time and to save a certain amount of suffering, I am leaving those out for the moment. I'm really, really sorry about leaving out 12. I was working with somebody in my home yesterday, and we jolly well did 12 together. But it's somehow, when I'm sitting one-on-one with somebody, I feel able to move forward more easily than when I'm with a crowd. So anyway, I want now to talk about intervals. Intervals. And I want to tell you what we mean by an interval. A set, which means a set of real numbers. So I'll write of real numbers. By the way, I want to give you a little bit of convention. If we ever talk about the set of real numbers, it's understood that we mean the set of all real numbers. But if we say using the indefinite article, a set of real numbers, we mean any old set whose members are all real numbers. You understand? A set of real numbers is said. If you see the words say with the passive said, or write, or written, or call, or define, you are looking at a definition. You understand? Another way you can see that you're looking at the definition is the heading. It's in front of your nose. A set of real numbers is said to be, and here's the word, interval, if, here we go, either a set, I think I need a name. I think I'll call it E. You know why capital E is so common with sets?
Second letter of set.
Nah, it's not the reason. It comes from the French. The French word for a set is ensemble. That's historically why the capital E is used. You know, speak English, you probably want an S, right? So it depends on mood. All right. A set E of real numbers is said to be an interval if either E is empty, the empty set is included, you see, or E is the set of all real numbers, or for some number C, we have E is the set of all real numbers below C, right? Or for some number C, we have E is the set of all real numbers less than or equal to C. You understand? Or for some number C, we have E equals the set of all real numbers that are greater than or equal to C, or what do you think's coming? For some number C, we have E equals the set of all real numbers that are greater than C, or anything else?
Could have an interval from C to B.
From A to B.
Yeah, for some numbers A and B, we have E equals the open interval running from A to B, or what?
Intervals.
I'm going to do what I should have done in the first place. Paste. For some numbers A and B, E is the interval running from like this. Or what? For some numbers A and B, E is which way?
Goes left side.
This way?
Yes.
Or for some numbers A and B, we have E is
Double close.
and those are the sets that are called intervals. Okay? Yeah, there is a shorter way of saying this. But I decided to write it out in all its gory detail. By the way, I can leave out this because it would be automatic. Because when you know what that stands for? It stands for the set of numbers x for which A is less than x and x is less than B. So if A is bigger than B, that would be empty. So the empty set would sneak in, you see. But I decided to make it explicit.
What if A equals B?
If A equals B, this one's empty. If A equals B, this one is what?
A, B, that.
This one will be singleton B, wouldn't it?
The next one will be singleton A.
And this one will be singleton A, and this one, if A equals B, is singleton A, and it's also singleton B. See, anyway, all right. Okay. Now, I'm going to tell you an obvious fact about intervals. An obvious fact. Here we go. Suppose that S is I've gone back to English language. S is an interval. And that P and Q belong to S, and that X is a given number, and that X is less than P, less than Q. Suppose that S is an interval, maybe any one of these situations, and P and Q belong to the interval, and what did I write? I want X to be between them. That's what I meant to write.
X belongs to S. Or they just give it a number.
Then X must belong to S. If you have an interval and you take two numbers in the interval and you take a number in between them, then that number will automatically be in the interval. Isn't that reasonable? I tell you what, let's prove it for this case. This is going to get very boring quickly. Yeah.
When we talk about intervals, are we talking about order? Like, are the numbers in order?
We're talking about real numbers, so we're talking about the usual order in the real numbers. They're very much subject to the order. So, for example, if you're talking about complex numbers, better not talk about intervals, you see. You can talk about intervals in any what we call totally ordered set. But the set I have in mind here is just a number line. And I'm talking about the so-called usual order, okay? So now, what if the set was this? It's the set of all numbers less than C. Well, if P and Q are numbers both less than C, then a number between them is also going to be less than C. Isn't that obvious? I think that in every one of these situations, I think it's an obvious fact that if you have an interval and you have two numbers in the interval, then a number between them has got to be in the interval. Is that a reasonable idea? Let me tell you, this is much harder. We're going to do something much harder. In fact, I'll say, much harder direction. I'm going to say we are given a set S. And we are given that whenever P and Q belong to S and P is less than a number X less than Q, the number X must belong to S, given. We want to prove that S is an interval. Let me get rid of Skype. We are given a set S, and we're given that the condition that I wrote over here works. In other words, what is the condition? That a number that is flanked on either side by members of S has got to be a member. That you can never have a non-member with a member below and a member above. If you're a number, and then there's a member of your set, of the set below and also some member above, then that number got to be in the set, given. We're going to prove that the set is an interval. And this is harder. And we're going to look at a bunch of cases. We'll be lucky if we finish it today. So, we want to prove that S is an interval. So here we go. Let me just see. Yeah, okay. I think I'll put a little heading. The case in which S is unbounded above and unbounded below. That's the case. I'm going to ask you a question. You've got a set S, and the given information is what? That every number that lies between two members of S is guaranteed to belong to S. That's the given information. And the set S is unbounded above and unbounded below. I'm going to ask you, what do you think this set has to be?
The set of all reals.
It's got to be, the set is unbounded above and unbounded below, right? And any number that lies between two members has got to be a member. We are going to prove that S is equal to the set of all real numbers. That's this case. You understand? That'll be an interval, will it not? When we're finished with this, I will worry about when the set is unbounded below and bounded above. Then I'll worry about bounded below and unbounded above. And then I will worry about bounded below and bounded above. And I think by that stage, if you can still, right? So, What must you do to prove that S is the set of all real numbers? To prove that S is the set of not just any old set of real numbers, but S is the set of all real numbers, you've got to prove that every number belongs to S. What must you do? I'll tell you what, I will put this. We need to explain why every number must belong to S. I thought I would say that before I get going. Folks, how do you prove for every? You want to prove that every real number eats chocolate. Suppose that X is a real number. No, not suppose X is a chocolate. Right? Suppose that X is a real number. Now, what do we know? The set S is unbounded above, right? So I'm going to tell you something. Using the fact that S is unbounded above, what does that mean?
There exists a member of S.
I know there exists a member of S above X, isn't that right? And when something exists, you can write? Choose. Choose a member, and I'm going to call it Q, of S such that X is less than Q. Yes? Very well. Using the fact that S is unbounded below what? Choose what? A member P of S such that what? Such that P is less than X, right? Now we have P less than X less than Q, and P and Q belong to S, and we conclude that X belongs to S. You understand? This is the case in which the set is unbounded below and unbounded above. In this case, the set is definitely an interval because it's the set of all real numbers. Okay? Very well. I'm going to do one more, and then maybe I can leave you to try and write one or two of the others. And you tell me on Wednesday that you need help, I'll write you one more. The case. Oops, too big. The case. Come on. I'm not capitalizing. Drive me crazy. In which S is bounded below and unbounded above. Reasonable? I would like to point out, of course. You know what of course means? Of course means don't be stupid, it's clear. Right? It's a very bad thing to write in a proof. It's insulting. I sneaked it in. Of course, S is non-empty. Why? I shouldn't. You never write of course. It's a terrible thing to do. I did it. Of course sneers at people. You shouldn't do it, right? Look, it's got to be non-empty because the empty set is bounded above and below. Trivially, you see. The set's not bounded above. It better not be empty. You understand? Okay. S is non-empty and it's bounded above, below, right? It's bounded below. Okay. We define C to be inf S. We can do that? Okay. Please understand a number less than C can never belong to S. Why not?
It's a low amount.
C inf S is a lower bound of S. There can't be members below, right? I want to explain why every number greater than C must belong to S. Okay? That's what I'm going to explain. Does it seem reasonable? How do you prove that something happens for every? What am I about to write? Suppose that X is greater than C, right? Okay. Using the fact that X is not a lower bound of S, how do you know X is not a lower bound of S? X is greater than the greatest BMW argument. It's greater than the greatest lower bound, so it's not a lower bound, right? Not a lower bound. Using the fact that X is not a lower bound of S, what can I do? Choose a member P of S such that P is less than X, right? Okay, using the fact that X is not an upper bound of S. How do you know that? There is no upper bound, so X can't be one. There are no birds to fly, right? Using the fact that X is not an upper bound of S, it's sort of like coming back there, right? Choose what? Choose a member Q of S such that X is less than Q. So now we have P is a member of S and is less than the given number X, less than Q, which is a member of S, and so X belongs to S. Do you understand? So I have fulfilled my promise. You see? Numbers greater than C got to belong to the set. Numbers less than C never belong to the set. What about C? I have no idea. You understand? We have shown that either S is the set of numbers greater than or equal to C, or S is the set of numbers greater than C, because all numbers greater than C do belong. Numbers less than C never belong, and C, I have no idea. So if C belongs, our set is this, and if C doesn't belong, our set is this. Do you understand? Now, this heading, and this is, I'm writing the heading, but I'm not doing it. What am I going to write? Enjoy. You are going to write this one, right? And there's one more.
Double bound.
You may need my help here. I'm not sure. Give it a bash. This one I know you will write after you've rewritten that one 5 times. You see? This one, let's see. I wonder if my email will buzz on that one. We'll see what happens. Okay, folks? All right.